Yeah, thank you for the introduction. So I will give today the lab tour on transmission electron microscopy, and yeah, my talk will give now introduction to this topic. Okay, I guess everybody of you knows light microscopy, right? Hope so, at least. And light microscopy is basically a good way to explain how electron microscopy is working. So in light microscopy, we have a light source, and we collect the light using a condenser lens and focus it to our object. So then we create an increased or magnified image of this object using the objective lens, and we can observe this image using the ocular, for example. Then, using the light microscope, we can see cells, we can visualize the stinger of bees, or we can look onto algae, for example. However, if we want to see smaller things, then we have to think of some other techniques. For example, if we consider an object or two objects that are apart distance d, then these guys, Ansgar Abe and John Strutt Rayleigh, they found an equation that relates this distance between these two objects with the wavelength, the refractive index of the material around the object, and the angle alpha with which the light is collected. For light with a typical wavelength of 500 nanometer, we find that we get a resolution of 250 nanometer. So when we want to see smaller things, then we have to change something. So the refractive index typically is always something like 1 or maybe 10 at maximum. So this is still quite small, so we cannot do a lot with this by changing n. We can also change this angle, but the sign restricts this also to maximum 1. So the way we need to go is the wavelength. And if we want to change the wavelength, then this guy, Victor de Broglie, comes into play because he found a relation between the wavelength of the wave that describes the propagation, for example, of massive particles with its momentum. So let's calculate this momentum. So if we start with the total energy here on the left-hand side, and this total energy is in principle the kinetic energy E times the acceleration voltage U plus its rest energy. So that's the rest energy of the electron in our case. Then we can solve this for the momentum, and we can insert this equation into de Broglie's law, and we end up with this equation here. So if we increase the acceleration voltage, then the wavelength will decrease. And this is what is plotted here. So lambda decreases with an increasing acceleration voltage. So for acceleration voltage of 300 kV, we can calculate a wavelength of 2 picometer only, which is basically 6 orders of magnitude smaller than what we have calculated previously for light. In fact, transmission electron microscopy is not that good. So typical resolution we can achieve in our machine is 65 picometer at a voltage of 300 kV. Okay, a little bit of history. Transmission electron microscopy was developed in 1931 by Max Knoll and Ernst Ruska. And Ernst Ruska received the Nobel Prize for Physics for that in 1986. So this is basically their experiment, what they did. So they had two electron magnetic lenses, and they had two objects in there. If they only switched on the first lens, they could get a magnification of 13 times of the object 1. If they only used the lens 2, they could achieve a magnification of 4.8 with this lens, and if they could combine the two lenses, they found a magnification of 17.4. This is not very impressive, but it was the first steps in electron microscopy. So they could show that you can use electromagnetic lenses to get a magnified image. This is how an actual electron microscope looks nowadays. So it's a little bit more complicated than in these days. It has it starts with an electron gun and an accelerator. So this is basically the light bulb of the electron microscope. Then we have a monochromator here for a monochromator. Then there is a condenser lens system which focuses the electrons to the specimen, which is basically here, situated in this plane here. Then in between there's a corrector for the illumination in this case. I will come to this later, again, for what it's good. And then we have projector lenses with which we can have a more magnified image of the specimen. And we have further ADX detectors or detectors, for example, energy dispersive X-ray spectroscopy, and we have further cameras. Okay, let's go through the TEM step by step. First of all, we need the electrons, and usually the electron source is a typical Schottky field emitter. So we have a tungsten crystal, and if we consider such a crystal, we see that the energy or the potential in this crystal, or the Coulomb potential, is just looking like this. So we have a periodic arrangement of this potential which stems from the different atoms that are in this tungsten crystal. So now we consider the electrons which are bound in this crystal, and at a low temperature, like room temperature for example, they are distributed in the crystal according to Fermi distribution. So what we see is the only few electrons are above the Fermi energy. So that means in principle no electron can just escape the material. So we have to do something about this. And what we do is, first we can heat the specimen. So then the Fermi distribution will widen and we get more electrons above the Fermi energy, but still it's difficult to get significant electrons out of the crystal. Next step is to apply an electric field to this tip, and that will reduce the work function of the material, so that in principle some of the electrons, they can leave the material. These electrons are then accelerated to these 300,000 volts. The next device was a monochromator. In principle, I said that the electrons are thermally, this is a thermal effect that helps to escape the electrons from the crystal, and therefore they have a finite width of their energy. So they have a finite energy distribution. Typically this is around 1 electron volt for a typical setup, but sometimes you want to have a smaller energy width, because this energy distribution will lead to aberrations in the machine that are called then chromatic aberrations. So you want to reduce these chromatic aberrations, and you can do this by, for example, reducing this energy width. In our machine we can reduce it to about 150 milli-electron volts. How does it work? Basically, we apply a magnetic field, so the electrons are coming down on the optical axis. That means, the velocity vector, I count it upwards because electrons are negatively charged. The magnetic field looks into viewing direction, and that means a Lorentz force is acting, which points to the door there. But if the Lorentz force would point just into the direction of the door, then the electrons would be deflected in this way, and they could crash into the column, which we don't want. Therefore, we apply an additional electric field which compensates for this Lorentz force, and then afterwards electrons with a velocity v0, they will going down on the optical axis, whereas electrons with a larger velocity or lower velocity than v0, they will be crashing into an aperture, and in this way we can select or we can make a smaller energy distribution of the electrons. Another advantage of this monochromator is that we can basically tune continuously the electron beam from 20 nanoampere down to few picoampere. This is important because sometimes specimens can be beam sensitive, and if we would apply too high beam current, then we would damage the samples, what we don't want, because we don't want to change the object of the investigation. After having passed the monochromator, we will enter the condenser lens system, and then it's the point where I need to say something about the lenses we use. You can imagine we cannot just use a glass lens like in a light microscope, because the electrons, they will be stuck in the glass and they will be lost. So in electron microscope we have magnetic lenses. So we have in principle we have a lens coil, a lens coil, and we have a yoke. So the lens coil will produce a magnetic field, which then is basically emitted, which points out of the yoke, and this field here in the middle, which is visualized like here, will lead to, first of all, that the electrons are going down a spiral in the microscope, and because the magnetic field is inhomogeneous, it will have a focusing effect. This here shows in principle an actual electromagnetic lens, which we have built, which we took from an old microscope. So basically we have here the coil, the lens coil. I can give it a round. And this one is basically the yoke, where you can see where the electron beam is going through. And yeah, there's an upper pole piece and the lower pole piece. Unfortunately, I cannot subdivide this at the moment. Okay, so in fact we have in the spectra microscope, we have actually 5 different lenses in order to that build up the condenser lens system. And with these 5 different lenses we can realize 2 basic modes. One is conventional transmission electron microscopy, and then in this mode we build up a parallel beam, so we illuminate the specimen or the area of interest in a parallel manner, so the whole area is illuminated. And this is a mode, was the original mode that was invented by Max Knoll and Ernst Ruska. There's a second mode, which is called scanning transmission electron microscopy. Here we have a convergent illumination. That means we focus the beam to very fine probe, so as small as possible, and then we can scan this electron probe over the specimen using deflection coils. This mode was invented by Manfred von Ardenne in 1937. Okay, so then we have already arrived at the specimen. And of course, because electrons, they have a strong interaction with matter, so we need to do something with specimen preparation, because we cannot just enter a tool or material like this into the transmission electron microscope, because electrons will get stuck in this material. So depending on what material we have, there are different specimen preparation techniques. For example, if you come with a powder of nanoparticles, for example, then which have a thickness in the range of about 10 to 50 nanometer maybe, then it's enough to disperse the powder on carbon-coated copper grids. This, for example, shows such a typical grid. So we have there's this grid, this copper, and in between we have very thin carbon film on which we deposit then the particles. For biological samples, okay, this is not really our expertise, but typically biological samples, they are covered in a resin and then cut by ultramicrotomy. If we have a larger part like this, we can cut a small part of it, then we can grind it, and we can grind it very thin to about maybe 5 micron, and then we can ion etch this small part until we have a small hole in the middle, and in the vicinity of the hole we will get electron transparent areas. If we have more complicated samples, for example, if you have samples from semiconductor, where you have maybe a transistor or something like that, then you are interested maybe in a special transistor, and then you can say, yeah, but I want to have the transistor which is located here and not the transistor that is located here. Then we need some more sophisticated techniques, and this is then by focused ion beam preparation. I will come back to this focused ion beam preparation later during the lab tour. Okay, so now we have the specimen, and the specimen actually is located within the objective lens. So this is basically a view into the into the objective lens. So here we have the upper pole piece of the objective lens. The lower pole piece is a little bit hidden, but will be here. And here on the right hand side we see the entrance where the specimen holder is inserted like this. The electrons are coming down here and will go through the column. The objective lens has two important planes. One is, okay, of course, every lens has two important planes. One is the focal plane, and in the electron microscope, we have in the focal plane we have a so-called, we also call it diffraction plane, because we see here a diffraction pattern, and the diffraction patterns look like this. So every point here in this diffraction pattern corresponds now to a crystal lattice plane in our sample. So from these kind of images, we can learn something about the crystal in the sample. The other important plane is the image plane, and if what we have here is a real space image of our specimen. With the projector lens, we can then focus onto the diffraction plane and image the diffraction plane onto a camera or a screen or a detector, or we can image the image plane to the camera or the detector. So this projector lens system will make a higher magnified image as the objective lens initially made. Okay, so basically I'm now through the column, and then I want to repeat again the different modes that we have in transmission electron microscopy. As I said, we have conventional transmission electron microscopy, where we build a parallel beam using the condenser lens system, and then with the projector lens system we can decide whether we want to have a focal plane on our camera or whether we have the image plane on the camera. And depending on how I excite the projector lens system, I can have both. I can insert apertures either in the focal plane. For example, I can select a certain lattice plane, and with this I can then image can analyze certain defects that are in the crystal, because you can imagine if I make an image with a beam that belongs to certain lattice planes, and then the lattice planes are somehow disturbed, then I will get a darker contrast. So this is then called bright field or dark field imaging. On the other hand, I can also insert an aperture in the image plane and select a certain area, and then I can make a diffraction pattern out of this area, and this will help. So then I can analyze the diffraction pattern of a certain area. This is called then selected area diffraction. Okay, the other mode is scanning transmission electron microscopy. Here we typically have an electron beam focused to a point that is then scanned over by the deflection coils over the specimen. In the scanning transmission electron microscopy mode, we typically use the projector lens system so that the diffraction pattern is imaged onto the camera or onto the detectors. Okay. So, and as in the last years, it becomes more, the scanning transmission electron microscopy mode becomes more and more important compared to the conventional transmission electron microscopy mode. I will focus more on scanning transmission electron microscopy in the following. One of the most important detectors that we use in scanning transmission electron microscopy is the high-angle annular dark field detector. It means, so this in principle shows the side view of the detector. So we open the column on the side, and then we see here the detector. In fact, it's a glass tube where we have a fluorescent layer on top, and if an electron hits this fluorescent layer, it will emit some photons, and these photons are traveling along this glass tube, and then there is a photomultiplier and then some electronics that detects these photons. You might have noticed that there is a hole in the middle, and this is because we are not interested in this mode in the electrons that are going straight through, so or are scattered only into small angles. We want to have the angle, the electrons that are scattered to high angles. And annular means that we have averaged it around the detector in a sphere, in a circle. Exactly. So why do we do it? Because in principle, okay, it's not perfectly correct, but it's a good example or explanation for it. So you might remember Rutherford scattering. In Rutherford scattering, Rutherford scattering is basically proportional to the square of the atomic number of the material of the material or the elements in the sample. That means if there is a heavier material somewhere, then more electrons will be scattered, or the scattering will be stronger into these high angles, and therefore we get a higher intensity in these areas. And that makes basically the contrast of the high angle and a dark field detector highly chemically sensitive. This can be in fact used to measure the concentration, for example, in semiconductor heterostructures, what we did some years ago. Okay, then there are different segmented detectors. Here is an example of what we have in our machine. It's a so-called Panther detector, and it consists basically out of two different detectors. There is in this first, in the smaller detector, we see that there is no hole, but we see that we would detect here on this detector electrons that are unscattered, and this is called therefore a bright field detector. The image that results from this detector is quite similar to image that we would get in conventional transmission electron microscopy. If we would use this outer ring of the detector, then we would get an annular bright field signal, and this signal usually is very useful for imaging light atoms. So if we have, for example, oxidic materials and you want to study the oxide positions, then you would use the annular bright field. Then we have the second part of the detector, so this, as you see, it's already larger, and therefore we can, and has a hole, therefore we have here a dark field, we would create a dark field image, and eventually, if you would set up the camera lamp correctly, you could even make high angle and a dark field with this detector. Last technique, as we can also do here, is differential phase contrast. You might have seen that the detector is somehow segmented. It's not annular symmetric, but it has some segments. And this is what we use in differential phase contrast. So consider this detector here. So we have different segments, red, blue, green, and magenta. And if we put now the beam symmetrically on it, every of these segments will get the same intensity. But what happens if we have an electric field in the specimen? For example, the electric field points in this direction. The electrons will be deflected slightly. And that means the detector will see a different signal, red minus blue. So we will have a negative difference signal between red and blue. And the stronger the electric field, the stronger will be the deflection. That means we can basically measure the electric field, and from these different four different directions that we have, we can not only measure the magnitude of the electric field, but we can also measure the direction of the electric field. Okay, this is nice, but sometimes you don't know what exactly you want to evaluate, and maybe there are techniques with which you can much better analyze the direction and the magnitude, for example, of the electric field, and then you might be interested to have more pixel, and this can be done by fast cameras that are available nowadays. For example, we have the so-called MPAD detector installed in our machine, and it has a very high dynamic range, which ranges from 1 electron that we can detect in a pixel, so it has single electron sensitivity, and it can count up to 1 million electrons. We have a high frame rate of this detector, so we can measure 1,100 frames per second for 128 by 128 pixels. And then we record, of course, the diffraction patterns, and then basically here from this diffraction pattern we could then later in the post-processing we could select maybe the high angle annular dark field range, or we could segment this inner area and measure the deflection of the beam here. So for measuring the electric fields in the specimen. Okay, measuring electric fields is in principle possible even for electric fields in between the atoms, but for this we need very, very precise electron probes. And this only is possible because we have correctors for lens aberrations. As I said before, electromagnetic lenses are not very good, so because we have for example, we have a wavelength of 2 picometer, but the resolution is only 65 picometer in our machine. And this also already shows that electromagnetic lenses, that there can be still some, that there are some possibilities to evolve further. However, the state that we have at the moment is already quite good because of these guys, because they invented corrector systems for these aberrations of electromagnetic lenses. In principle, it's like that. Round magnetic lenses always are focusing. So you cannot build up divergent electron lenses, and that means you cannot really correct for aberrations. But however, these guys, they broke the rotational symmetry and used hexapoles or octupoles, and with these they could achieve a diverging effect of the magnetic lenses. And with this you can then start to correct aberrations in the machine. Just to show you an effect, there is made an example. So in fact for silicon, so this is a silicon crystal, so every ball here is a silicon atom, and if I turn this around by 45 degrees, then I will see in 1-1 Oder projection that I get some dumbbell-like structures. So you see pairs of silicon atoms which are sitting on this arrangement here. Okay, this is the structure, and now I took such a specimen with silicon and I went to our 2 machines that we have. We have basically a Titan microscope. This Titan microscope has a corrector, but not for the illumination system, but for the imaging system. So it's dedicated to conventional transmission electron microscopy. But the STEM mode we cannot correct in this machine. On the other hand, the Spectra machine that we have, it has the corrector above the specimen and in the illumination system, so we can correct for the illumination of the system. So this is dedicated to the STEM mode. And if I put the sample in, we can see in the Titan, that the positions here are a little bit elongated, and if you have a lot of fantasy, you might see that some of these points, maybe here, that they are a little bit separated. But it's difficult to see. Whereas if we go to the image of the spectra, it's quite clear that that these elongated structures that we saw in the Titan, that they consist out of 2 atoms, and this already resembles this model structure quite well. Okay, so I've not spoken about the interaction between the electron beam and the specimen up to now. So what happens? In fact, if the electron beam comes down, we can have elastic interaction with the specimen. So that means the electrons, they can scatter at lattice planes in our specimen. On the other hand, we have also inelastic interaction with the specimen. So that means the primary electron beam, it can hit one of the electrons in an atom of the specimen, and then it can kick out this atom. Not the atom, sorry, the electron. Of course, the primary electron will lose energy. Will lose energy. On the other hand, the atom, in the atom, there will be an electron from outer shell that will go to this inner shell, and it can emit either an Auger electron or it can emit an X-ray quant. And now we have detectors with which we can measure the energy of these X-ray quantas and count, of course, the number of these X-ray quantas. This technique is then called energy dispersive X-ray spectroscopy. This typically shows such a spectrum that we can get from this ADX detector. So you see that there are discrete peaks in there, and this is clear because the energy levels of the electrons in the atoms, they are discrete, and they are a fingerprint for the respective element that is inside. And therefore, these peaks, they are on discrete. These peaks, they are appearing at discrete energy positions, and from these energy positions, we can then say which elements it is. So here in this spectrum, for example, we found that there is manganese, phosphorus, aluminum, oxygen, and carbon in there. In modern electron microscopes, we can they have sophisticated detectors there. For example, in our case, it depends, in fact, out of 4 different detectors, ADX detectors, and they allow us now to measure such a spectrum for every scan point. So if I scan the sample, like here, this is the HADF, an HADF STEM image of nanoparticles, and for every of these scan points, we get such a spectrum. Now we can just focus on one of these peaks. For example, okay, this is does not belong to these maps, but for example, here we will see we have silicon, we found titanium, and we found cobalt. Okay, and then we can see, of course, the distribution. In this movie I like very much because it shows that the larger particles, they consist out of silicon and titanium, and then we have small cobalt particles in between these particles, in between the silicon titanium particles. In fact, we also see that these larger particles, they are not fully composed out of the mixture, but they phase separate, or the silicon and titanium, they separate in these particles. I said also that before, on the slide before the last slide, that the primary electron beam will lose energy when it kicks out an electron from the atoms. And this we can analyze. So if we, okay, not in this microscope, but in the Titan microscope, we have a so-called imaging filter. So the imaging filter looks like that. So the electron beam comes down, then we apply a magnetic field, and this magnetic field will, similar to the monochromator, will disperse the electrons with respect to their different energies. So slower electrons will deflected higher up, faster electrons will be deflected lower down. And that means we have here a plane where we will see the distribution of the electrons according to their energy. And this we can, of course, then correct. So then such a spectrum is called electron energy loss spectrum. And this looks such a typical example. We see here, for example, different edges in this spectra. For example, here, this is the oxygen K edge, and here at around 870 electron volt, we have the cerium L edge. From the height of these edges, we can infer the composition in the sample, and the shape of these edges. It can give us information about the oxidation state, for example. So cerium oxide typically can be in different oxidation states, and depending on the oxidation state, the ratio between these two peaks will change. So maybe for cerium 2+, it's like this, and for cerium 3+, the ratio will change. So then maybe the first is much lower than the second one. Furthermore, we can use the imaging filter in spectroscopy mode, but we can also switch it to image mode. That means in this energy selective plane, we can insert an aperture where we cut out electrons that have a certain energy loss. So only these, for example. And this then gives us an image. So with these electrons, we can make an image. And this gives then the distribution of the cerium atom. In a similar way, we could do it with oxygen. Unfortunately, this is not really visible here on the beamer. Similar for carbon, but carbon is not here now in the spectrum. So this technique is then called energy filter transmission electron microscopy. We can do further things. For example, because I said we can take diffraction patterns per scan point. So if we take a diffraction pattern for every scan point, we can then compare these diffraction patterns with a set of simulated diffraction patterns, so for different phases and different orientations. And then on a best match basis, we can then decide or find for each pixel the phase and the orientation of the material in this pixel. This is an example for that. This is an example for ruthenium, gallium oxide on ruthenium substrate. And here is the phase map basically. So we see we have ruthenium in the substrate, which is basically has everywhere basically the same orientation beside of this area here. However, in the gallium oxide, we see that there are different grains. For example, we have a green color, which corresponds to the beta phase of gallium oxide, and we have this cyan color here, which corresponds to the gamma phase. However, we also see that there are different grains here in the beta gallium oxide, and these different grains are due to different orientations. So, for example, beta gallium oxide is monoclinic, and the substrate ruthenium is hexagonal. And if we put now the ruthenium, this monoclinic beta gallium oxide onto ruthenium, it can orient in or it can align to the substrate in 3 different directions. And these are called then rotation domains. That means we have different rotation domains in this crystal. In a similar manner, we can do something that is called strain mapping. Again, we take diffraction patterns for every scan point, and then and now we do not compare directly with a database, but we measure in the diffraction pattern the positions of the diffraction disks. So, for example, if I put my electron beam here somewhere in aluminum oxide, then I have a diffraction pattern. Then I will detect the diffraction spots like this. If I put the electron beam in gallium oxide, for example, gallium oxide has a larger lattice parameter than aluminum oxide, then the diffraction disks, they will shift together, so the distance will be reduced. And this can be used in order to calculate the strain in the sample. So, for example, here we have gallium oxide layer on aluminum oxide, and this was overgrown with an indium gallium oxide layer. And then we can see, of course, the different strains. First, here a strain component in y direction, so that means maybe in this direction, and in z direction, which is here in this case the growth direction. Furthermore, we can also measure whether there are shear strains. That means that the reflections, they will shift together, so that they make such a movement. Or we can also see whether there is a rotation of the diffraction pattern between the layers. And that means we can get 4 different strains for each pixel. So quite a lot of data that we can produce. Very often samples can be considered as homogeneous in electron beam direction, but this is not always the case. Sometimes people are interested in the 3-dimensional structure of the sample. For example, here this shows a needle-like structure which was cut from a nanoporous gold sample. Nanoporous gold is usually produced from a gold-silver alloy, and this gold-silver alloy is put into an acid, and this acid will remove the less noble atoms from the alloy. In this case, the silver atoms have been removed, and what comes out is such a nanoporous structure. It works, yeah, okay. So now we can see, of course, how the ligaments are formed. We could measure from this 3D structure. We can measure the sizes of the ligaments and the pores, and we can do this even together with ADX. So then we can see that most of the parts are made out of gold, but we can also see that there are some areas where we have still some residual silver in this structure. And this, of course, is an important was an important information for the people who produce these needle-like structures. Oh no, the nanoporous gold, not the needle-like structure. Yeah, with this I'm basically through the presentation. And then I want to summarize that. So in principle I showed how TEM is built up, or the setup of a transmission electron microscope. I hopefully showed you that there are two different modes that we can use: conventional transmission electron microscopy and scanning transmission electron microscopy. We have different analytical tools available, so we can do energy dispersive X-ray spectroscopy in the TEM and electron energy loss spectroscopy. Transmission electron microscopy does not only produce nice images, it also can be used to quantitative evaluate things like the composition of the sample, so in form of concentrations. We can measure, for example, strain. We can measure electric fields, phase and orientation of grains. We can have a defect analysis, and this on length scales between few microns down to even in subatomic scale if we want to measure electric fields. And this, not everything, or some of these quantities we can even get in 2 dimensions or even in 3 dimensions. Yeah, and with this I want to thank you first for your attention, and I hope that we will see us in the lab tour, in the further lab tour. Okay, thanks.